Welcome to our last full week of class. Monday will be a review session. We're going to work through Chapter 8 this week, and this material will be on the final exam. There's going to be WebAssign, and there's a worksheet for you to work on, kind of the same way there was with Chapter 7. So that'll give you some good practice. Let me pin this so that you can see the announcements. For TU students, oh, by the way, it is time to go ahead and fill out student evaluations. Just check your student email, please, your TU email, and follow that link. That's important. I'd appreciate it. For TU students in this class, the final is Saturday, December 14th from 3 to 5 p.m., and it's in the Science Building 2226, and that's on the TU campus. For the couple of Tune students that are left in the class, it's going to be Monday there at Tune. The room is going to still, we're still figuring that out, but I'll be sure and let you know what room it's going to be. And it's probably going to be 2 to 4 in the afternoon on Monday afternoon. That does not conflict with other exams that are being scheduled. Okay. Nick, we can talk after class and make sure that we have you all sorted out. So tonight our goals are going to be to look in section 8.1. We're going to talk about binary relations, and there are two kinds of binary relations. One kind is from a set A to B. So we have two sets. And then another is on set A. And that's really just from A to A. We just say on set A. And we're going to look at, examples, of course, of these. And then in section 8.2, we're going to talk about properties of binary relations in the same spirit that functions have properties like one-to-one and onto. Binary relations have properties. And if they're on a set A, in other words, if they're from A to A, that's what on set A means, and we'll get those definitions tonight. And the three properties we're going to look at tonight are reflexivity, symmetry, and transitivity. And you probably have some idea about these properties, even if you might not have ever called them those particular names. If you're wondering about exam 3, it has been graded. I just got those scanned today on campus, and I'll be uploading them after class tonight. So you'll be able to get your test 3 results tonight. So let's do a little do now to get everybody warmed up. And the do now tonight will serve as our example 1. We're going to let A be the set that contains 2, 3, and 4. And we're going to let B be the set that contains 2, 3, 4, 5, and 6. And what we'd like to do for our warm-up is just find 3 different subsets of A cross B. 3 different subsets of A cross B. All right? And there are lots and lots of possible solutions. So just take a few minutes here and find 3 different subsets of A cross B. Okay. And since these are binary relations, we usually call them by capital curly letters like curly R. So we'll follow that convention tonight until we talk about a very special kind of binary relation. So anybody want to proffer up their first subset of A cross B? Does everybody know that the elements look like ordered pairs where the first coordinate comes from A and the second coordinate comes from B? I hope.
So for my set, I got the order pair 2, 3, and then the order pair 3, 3, then the order pair 4, 3.
Very nice. That is definitely a binary relation from A to B. It actually happens to be a function as well, but not every binary relation is a function. What is the largest subset of A cross B that we could possibly take? Anybody? Do you remember that every set is a subset of itself? So A cross B, the whole thing, is a subset of A cross B. So technically that is a binary relation from A to B. That's what we're actually looking at is subsets of A cross B. Turns out that's going to be what it means to be a binary relation from A to B. By the way, how many elements are in A cross B? How many ordered pairs would there be in A cross B for this A and this B?
15.
Well, we have 3 choices for first coordinates, and we get to mix and match with 5 choices for second coordinates. So how many ordered pairs are there in A cross B, everybody?
15.
Yep, 15 ordered pairs. So technically, that's a subset of A cross B. It's the biggest one. Here's another binary relation from A to B, or another subset of A cross B. Well, just 2, 2, just that single ordered pair. It is a subset of A cross B, so technically it's going to be a binary relation from A to B. And in fact, the empty relation is also a subset of A cross B, the empty set, because the empty set is a subset of every set. So here's the fact. So this was supposed to be the kind of the motivating example tonight. All of these are binary relations from A to B because the definition of a binary relation from A to B is simply any subset of A cross B is a binary relation from A to B. Now, we have talked about functions, and they're very special kinds of subsets of A cross B, where A is the domain and B is the codomain, right? But here, a binary relation doesn't have to be a function. Every function is a binary relation, but not every binary relation is a function. So let's get our definition now that we've warmed up a little bit. So we'll just get the definition of a binary relation from A to B. Here's the definition. Given sets A and B, any subset, so I want to just emphasize any subset of A cross B is called a binary relation from A to B. Okay. So let's look at another example. We can use the same sets A and B, but we can play a different kind of game. Let's say that A is the set again with the elements 2, 3, and 4, and B is the set with the elements 2, 3, 4, 5, and 6. Now we're going to define a binary relation with a rule. We define curly R, a subset of A cross B by this rule? Well, there are a couple of different notations, so I want to show you the notation. Of course, ordered pair notation, AB is an element of R, or another notation that we like is A, R, B. So this is a notational thing. It means the same thing as A, B is in curly R. We just say A is R to B, or A is related to B. If A divides B. So that's going to be the rule that's going to tell us when A is related to B, or when AB is in this relation curly R. And now we're going to find curly R as a set of ordered pairs. We have a rule, and now we can use the rule to figure out which ordered pairs are in this curly R, this relation curly R. All right, so here's our solution. Let's do this together. It's a set, so we'll use set brackets. The elements are ordered pairs, of course. So what we're going to do is we're going to look at each element of A, and that's the little a, the first coordinate of a potential ordered pair. And we're going to ask, hey, which of these elements of set B can serve as a second coordinate when the first coordinate is little a equals 2? In other words, for which of these elements of set B does A divide B when A is 2? So can anybody tell me one of the ordered pairs that'll be in this binary relation?
2, 2.
Yeah, because 2 does divide 2. Does everybody understand that that's why 2, 2 is in there? Good. But there's some other elements of B that can pair up with 2 as their first coordinate. Remember, 2 is coming from A. What other elements of set B could serve as a second coordinate to make this rule A divides B true? Yep, good, Danny. 4. Excellent. Any other elements of set B that could serve as the second coordinate when the first coordinate is 2 from set A?
2, 6.
Yep. And I think that exhausts the ordered pairs that have 2 as the first coordinate. So then we move on to the next element of A, namely 3, and we play the same game. We want to find the ordered pairs that have 3 as the first coordinate and one of these elements from B as the second coordinate. Are there any possible elements from B that could serve as the second coordinate if the first coordinate is 3?
3.
Yep, because 3 divides 3. Good. Any other ordered pairs with 3 as the first coordinate, folks? That's right, 3, 6. Nice, Danny. Any other ordered pairs with 3 as the first coordinate? That's right. There aren't any other elements of B that are divisible by 3. So then we move on to the next element of A, the last element, 4. If 4 is our first coordinate, little a, is there an element, little b, here in set B that can work as the second coordinate? If the first coordinate is 4?
4.
Yep. And that's it. So notice this is a binary relation from A to B, but it's certainly not a function, is it? Right? It breaks the definition of function because some of these elements from A are pairing up with more than one element from B. All right, so there's a very short WebAssign that I'll put up right after class, and it's got 4 or 5 problems from section 8.1, and it'll help you practice this. We're going to look at numerous examples, but the really interesting examples come about when we talk about a binary relation on a set A. So let's go ahead and get the definition so that we know what we're talking about here. Given a set A, any subset of A cross A is called a binary relation on A. So instead of saying it's a binary relation from A to A, we just shorten that and say it's a binary relation on A. And here's some notation. Again, we say A is related to B if and only if the ordered pair A comma B is in the relation. And this is for all elements, little a and little b, coming now from set A. Both A and B, these little coordinates, come from the same set. So let's look at another example now. All right, we're going to do a big one. We're going to let A be this set. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in it. We're going to define a binary relation on A. We're going to call it curly R as follows. Here's the rule. Little a, b, so the order pair a, b is in curly R if and only if A mod 4 is equal to B mod 4. So this is a good review for the final. Of course, the question would be to find curly R. And let's just review what A mod D looks like. So just recall, if we're given integers, A and D would not equal to 0. So A and D is not equal to 0 because that's our divisor. A mod D is equal to the remainder R. Remember, it's the remainder, where the quotient remainder theorem is that A is equal to D times Q plus R, where 0 is less than or equal to R, and R is strictly less than D. So A mod D is the remainder that we get when we divide A by divisor D. Does that sound familiar? So our divisor, when we're talking about A mod 4, is of course 4. And what we're saying is 2 elements of this set A are going to be related to each other. A is going to be related to B if and only if the remainder we get when we divide A by 4 is equal to the remainder that we get when we divide B by 4. All right? So this is really going to be very good review. Let's see if we can start thinking about what this curly R would look like. Do you remember when we were talking about the QR theorem, how we talked about dividing by 2 and it split the integers up into 2 subsets? It partitioned the integers actually into the set of subsets where one subset was the evens and one subset was the odds. And if D was 3, then there are 3 different remainders, 0, 1, and 2, right? What are the remainders when D is 4? What are the possible remainders? That's right, 0, 1, 2, and 3. Very good. So as we start to build R, and this is a big set to build on, but it'll kind of start to get easier here in a few minutes. We're first going to look at 1, and we're going to think about the remainder that we get when we divide 1 by 4. And then we're going to look and see what elements in A have that same remainder. So let's just do a little scrap work over here in the border here. If we're dividing 1 by 4, 1 is equal to 4 times some quotient plus some remainder. What is the quotient and what is the remainder when we're dividing 1 by 4?
The remainder is 1,
The
and
remainder is 1.
to divide it would be 0.
Yep, the quotient is 0. So when we divide 1 by 4, we get a remainder of 1. And in fact, certainly that's the same remainder as we get when we divide 1 by 4. In other words, 1 is definitely going to be related to itself because 1 mod 4 is definitely equal to 1 mod 4. In fact, this equality here is going to make things work out really nicely for us here in a minute. So let's just think about other integers here in this set that yield that same remainder and that will be related to 1. What other elements of A yield a remainder of 1 when they're divided by 4?
5.
Yeah, 5 is 4 times the quotient 1 plus the remainder of 1. So 5 has the same remainder that 1 does when it's divided by 4. So 1 is related to 5. And in fact, 5 is related to 1. This is called symmetry. 1 is related to 5, and 5 is also related to 1 because of the nature of what equality means. Equality doesn't care whether the B mod 4 is on this side of the equal sign or the A mod 4, right? So if A mod 4 is equal to B mod 4, then B mod 4 is going to equal A mod 4. In other words, 1 is related to 5, but 5 is also related to 1. And 5 is going to be related to itself because it yields the same remainder as itself when divided by 4. That remainder is 1. Are there any other elements of set A that yield this remainder of 1 when they're divided by 4?
9.
That's good, 9. 9 is 4 times the quotient 2 plus a remainder of 1. Well, guess what? That means 1 is going to be related to 9, but 9 is going to be related to 1. 9 is going to be related to 5, and 5 is going to be related to 9. It doesn't matter what order we put these in, they're all related to each other. And then 9, of course, is related to 9. So something very special is happening here. 1 is related to 5, 5 is related to 9, and 1 is actually related to 9. This is called transitivity. Equality is very special that way. Are there any other elements in set A that yield the same remainder as 1, 5, or 9 when divided by 4? I think that's it. So now we move on to 2. Let's think about 2. What is the remainder that we get when we divide 2 by 4? And we're going to try to figure out what it's related to. What other numbers yield whatever remainder it yields?
2.
Yep, it yields a remainder of 2 because the remainder is always going to be in its own class of integers yielding that remainder. 4 times 0 plus 2. So 2 is certainly related to 2 because 2 mod 4 equals 2 mod 4. What other integers give a remainder of 2 when they're divided by 4? There's going to be some other ones that have a remainder of 2.
10.
That's right. I'm going to put it here. There's one in between. Because 10 is 4 times 2 plus a remainder of 2. What's the one in between?
6.
6. Very good. Because it's 4 times 1 plus 2. These 3 all, see how they're 4 apart, just like 1, 5, and 9 are 4 apart. Remember how that works? Every fourth integer would have the same remainder as the one 4 behind it and 4 in front of it. So let's see, we got to write a bunch of ordered pairs. Okay, so 2 is related to 6. 6 is related to 2. 6 is related to 6. 2 is related to 10. 10 is related to 2. But 6 is related to 10. And 10 is related to 6. And also 10 is related to 10. Did we get them all? There should be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. All right, what's the next integer that we should deal with? Remember how we did this? We started with 1, figured out all the integers that were related to 1. Then we looked at 2 and figured out all the integers in this set A that are related to 2. What's the next one we should look at?
3.
Yep. 3, when divided by 4, yields a remainder of 3 because it is 4 times 0 plus 3. So we can sure add 3 being related to itself. It gives a remainder of 3. So what other elements of A are going to give a remainder of 3 when we divide them by 4? That's right, 7. 7 is 4 times 1 plus 3. So since 3 and 7 have the same remainder, mod 4, right? 3 is related to 7. 7 is related to 3. And of course, 7 is related to 7. We are almost done. What's another integer that we haven't played with yet?
4.
That's right. 4 is, of course, 4 times 0 plus 0. Because when we divide 4 by 4, we get a remainder of 0. So 4 is related to 4. Are there any other elements in A that give a remainder of 0 when they're divided by 4?
8.
That's right. 8 is 4. Wait a minute. This shouldn't be 0 here. What should it be? What's the
1.
quotient? Yeah, this should have been a 1. Because when I saw a 2 here, I'm like, wait a minute, where's the 1? 8 is 4 times 2 plus 0. So 4 is related to 8 because they both give a remainder of 0 and they're divided by 4. And 8 is related to 4. And finally, 8 is related to 8. And that is it. Every single integer appears in some of these ordered pairs when the integers are ranging from 1 to 10. Questions? Now it seems really huge, right? This binary relation's got what, 9, 18, 20, it's got 26 elements. Holy cow, 26 ordered pairs. It seems really big. But let me ask you this. It's a subset of A cross A. Do you agree? How large is the largest subset of A cross A?
100.
That's right. How'd you get 100, Nick?
10 times 10.
10 times 10. 10 choices for first coordinate multiplied by 10 choices for second coordinate. So, I mean, there were 100, right? We only found 26 that satisfied this rule, okay? This is a very special kind of binary relation. It has the properties that we're going to be talking about very soon. Tonight, it's got reflexivity and symmetry and transitivity. But what I'd like to do before we talk about those particular properties is just show you that we can build out this example and see our first infinite binary relation. Let's look at an example of an infinite binary relation on a set A. But of course, to get an infinite binary relation, we have to have an infinite set A, and that A that we're going to play with is the integers. That'll do. It's infinite. And here's the rule. The rule is very similar. For all A and B in Z, we say A is related to B, or little a comma b is in R if, all right, now there are two ways we can play the game. We can say if A mod 4 equals B mod 4. We can play it with that rule. All right. Just like we did before with our finite example. But I want to just show you tonight that there's another way to define this relation where two integers are related if they give the same remainder when divided by 4. So, or equivalently, here's the other way we can define this. 4 divides the difference A minus B. These two rules yield exactly the same binary relation on Z or on any subset of Z, as a matter of fact. We could have used this rule in example 3 up here. We could have, because think about it. When we were figuring out the ordered pairs that were in the binary relation curly R from example 3, integers were related if they were separated from one another by jumps of size 4. See, 1, 5, 9. 2, 6, 10, 3 and 7, 4 and 8. In other words, two integers were related if the difference between them was a multiple of 4. Do you see that? This is the standard way that we define what's called congruence mod 4. Now, even though we haven't proven that this relation is an equivalence relation, I think based on this, you can understand that something happens when we split up the integers by this relation. So I'm going to ask this question. It's sort of a sneak preview. Find the partition that this curly R induces on Z by finding the subsets of Z produced by grouping integers together if they are related to one another. See, we saw in our first example how if one was related to 5, then 5 had to be related to 1. And if one was related to 9 and 5 was related to 1, then 9 had to be related to 5. And 9 had, they were all related to each other. And so I just want to remind you that we did this when we talked about the QR theorem. We drew pictures of circles that represented the integers, and we did this for divisor D equal 2, and we did it for D equal 3. I think we might have even done it for D equal 4. We did it for the general case D, where we got kind of what looked like a pizza pie. But when D is 4, remember how it splits the integers up into 4 subsets? and they were called 4z. These are just the multiples of 4. They were also called 4z plus 1 for the multiples of 4 plus 1. These are the integers that had a remainder of 1 when you divided by 4. Then there was 4z plus 2 and 4z plus 3. Do you remember that? Do you remember doing that a while back? Well, this is the binary relation that induces this partition. If, all of the elements that have a remainder of 1 live in this quarter of this pie. All of the integers that yield a remainder of 3 when divided by 4 live down in this quarter of the pie. And every integer lives in one of these. And each integer only lives in one of these, because when you divide an integer by 4, you can only get one remainder. We get the same answer every time we divide a particular integer by 4. Remember, that was the kind of silly thing that the quotient remainder theorem said. It said we get the same answer every time we divide an integer by d. Just depends upon that integer and on d. And so this actually does form a partition. And it turns out that when a binary relation has the 3 properties that we're going to talk about tonight, then that binary relation always does this sort of thing, where it splits the set up into partitioned subsets. The partitioning sets are the classes where elements that are related to each other all live together in that subset. Any questions before we move on? Let's talk about these important properties. We're actually in section 8.2 now. Properties of a binary relation on A. So we have to stick with A for both the first and second coordinates to play this game. So for all of these definitions that we're going to learn tonight, we're going to let A be a set. And suppose curly R is a subset of A cross A. That means it's a binary relation on A, i.e., curly R is a binary relation on A. We have to have that to play this game. All right, so the first definition is for reflexivity. We say curly R is reflexive. That's what we're defining, what it means for it to be reflexive. If, okay, there are 2 ways we can write this. First way we could write it is this: for all elements little a in set A, little a comma little a is an element of curly R. Or we could write it using the other notation, A is related to itself. Okay, that's what it means for a relation to be reflexive. It's like each element of the underlying set looks in a mirror and sees itself. So that's why it's called reflexive. Okay? Each element is related to itself. A is related to A for every element in the set, big A. All right, now symmetry. We say curly R is symmetric if, now for the definition of symmetry, we need 2 elements of the set big A. So we'll say for all little a and little b in set A. And this definition is an if-then definition. It goes like this: AB being an element of curly R implies that B comma A is an element of curly R. Or if we want to write it using our relation symbol in between the elements, which is a really nice way to write it, A related to B implies that little b is related to little a. You can see why we like this notation. Finally, we have transitivity. We say curly R is transitive if, okay, so now I'm going to try to do something to help you remember this and these definitions. Reflexive, symmetric, transitive, RST. So we might, abbreviate these. R, not curly R, just R, S, and T. RST 1, 2, 3. Why am I saying 1, 2, 3? The definition of reflexivity requires one element of A. The definition of symmetry requires two elements of set A. The definition of transitivity is going to require three elements of A. So 1, 2, 3, RST. Here we go. For all little a, little b, and little c in set A, and again, it's going to be an if-then definition, but it's a little more complicated. We have a compound hypothesis. It goes like this. A comma B in curly R and B comma C in curly R together imply that A comma C is in curly R. Or using our other notation, A related to B and B related to C together force A to be related to C. So in some sense, what's happening with transitivity, folks, it's like this element B in the middle here is like a crossover element. Transitivity says, hey, if you've got B as the second coordinate in one ordered pair, and it's the first coordinate in another ordered pair, you should be able to cross over on the B and get that A is related to C, or AC is in the relation. Does that make sense? We're going to look at some examples. All right, so RST 1, 2, 3, here are our definitions of reflexivity, symmetry, and transitivity. Let's look at an example. Example 5. We're going to let A be the reals. So this is going to be an infinite binary relation. We're going to define the less than relation, less than, and we're going to denote it by curly L on R, the reals, as follows. For all X and Y in the reals, X is going to be L to Y if and only if X is actually less than Y. That's why it's called L. It's the less than relation. All right, and the reason I've picked this particular relation is it's a relation that we all understand really well. We all understand exactly what it means for X to be less than Y. It means X is to the left on the number line from Y. So, of course, the question is going to be this, since we're trying to study these properties, for each of the three properties, and these properties are, reflexivity, symmetry, and transitivity, RST, either prove the less than relation, curly L, has the property, or give a counterexample to show that curly L does not have the property. Okay? It's a real simple relation, and it's a good way to practice the definitions of reflexivity, symmetry, and transitivity. All right, here we go. Let's think about reflexivity first. So for the less than relation to be reflexive, it means for every x in the reals, x has to be L to x. In other words, x has to be less than x. Is that going to be true for every real number, x? Is x less than x?
No.
Not at all. In fact, it fails universally. We don't have to have a universal fail for a universal statement to be false, but here we actually have a universal fail. So all we got to do is pick our favorite real number, and we'll be able to say, hey, that real number is not less than itself. So pick your favorite real number. My favorite real number happens to be 3, but yours might be pi, or who knows what your favorite real number is. But we can just write it up. Notice whatever your favorite number is, I'll say 3, is in the reals. And 3 is clearly not less than 3. So, and here's some notation. I'm going to show you how we write not less than with the curly L. We say 3 is not L to 3. So we just take the curly L and put a slash through it, i.e. 3 comma 3 is not an element of the less than relation, so it fails to be reflexive. Okay. Now let's check and see if the less than relation is symmetric. In other words, if x is less than y, if x is less than y, does that force y to be less than x? What do you think it's going to be? Let's take a look. Here, I'm going to put our definition of symmetry up here where we can see it. And I'm going to put our definition of L where we can see it. Here's our definition. X is L to Y if and only if X is less than Y. Okay, that's our definition of curly L. So let's just see. Is it symmetric? Not at all. I mean, it's one of these relations that we understand. Just because X is less than Y, is that going to make Y less than X? Not at all. So let's give a counterexample. What about X equals 3 and Y equals pi? Right? Clearly, X is L to Y because 3 is less than pi. But Y is not less than X because pi is not less than 3. So the less than relation is not symmetric. It's not reflexive and it's not symmetric. Let me ask you this. If we were playing this game with the less than or equal to relation, would it be reflexive?
Yes.
It would be, because the equal to would allow us to always say that x is less than or equal to x. So it would be reflexive, but the less than or equal to still would not be symmetric. Questions? All right, let's look at the definition of transitivity and let's check and see if the less than relation is a transitive relation. Here's our definition of transitivity. If A is related to B and B is related to C, we should be able to cross over on the B and say that A is related to C. So we're going to be playing that game with the less than relation. So let's just think about it. If X is less than Y and Y is less than Z, are we going to be able to say X is less than Z?
Yes.
Yeah, we do it all the time because we understand what it means for a real number to be less than. It means it's to the left on the number line. So we're going to prove this one. Let's just write the definition of less than down for your notes in case you didn't realize this. By definition, X less than Y means X is to the left of Y on the real number line. So if we're going to prove transitivity, we're going to assume that X is less than Y and Y is less than Z for real numbers, X, Y, and Z. What do we wish to show? We wish to show X is less than Z, but that's just obvious. Since X is left of Y and Y is left of Z, I mean, that's the actual proof of the transitivity of less than. It's really just a physical representation of points on the real number line. Then X is left of Z. So X is less than Z. So we just showed that it's transitive. So the upshot here is that we just found out the less than relation is not reflexive, not symmetric, but is transitive. Okay, questions? I'm going to keep these definitions close by because now we're going to look at one of the most famous binary relations of all. It's so famous it has its own notation. Congruence mod n. It's a binary relation on Z. We have already played congruence mod 4 games this evening when we talked about two integers yielding the same remainder when divided by 4. In other words, 4 divides A minus B was what it meant for A and B to be related. That is the congruence mod 4 relation. But we can play this for any integer n that's greater than or equal to 2. So here's the definition. We say A, and this is the way we write it, triple equal sign with a little n underneath. And we read this congruent mod n to be if n divides A minus B. And this is for all integers, A and B. This is a binary relation on the integers. So the way we read it is we say A is congruent mod n to B, okay? And you can think of this divisor as being 2 or 3 or 4 or any divisor that's not 0, but we generally play it with n greater than or equal to 2. So this next example is where we're going to prove that this binary relation is an equivalence relation, but we're not going to call it that yet. That's coming. We're just going to prove congruence mod n is reflexive, symmetric, and transitive. Turns out any binary relation that's reflexive, symmetric, and transitive is what exactly we call an equivalence relation. And equivalence relations induce partitions on the underlying set, just the way we saw that partition of Z, where we split Z up into 4 subsets based on remainder. Well, congruence mod n in general is reflexive, symmetric, and transitive. So let's look at how it looks to prove that. So we'll just, go ahead and say, let congruence mod n be defined as usual. I'll just write it again. For all A and B in Z, A is congruent mod n to B if and only if n divides A minus B. So we're going to prove reflexivity, symmetry, and transitivity of this particular binary relation on Z. Okay. So there's our definition where we can see it. We'll start with reflexivity. Now, I've got to have a little room up here because I want to put the definition of reflexive up where you can see it. There's the definition of a reflexive relation. Notice what the hypothesis is. It's not an if-then definition, okay? It's a real simple definition. We just need to give ourselves an element of the underlying set, and what we wish to do is show that that element is related to itself, whatever the relation is. Here the relation is congruence mod n. So here we go. We just let A be an element of Z, because it's RST, 1, 2, 3. We just need one element of the underlying set, and that's Z. What do we wish to show? We wish to show that A is congruent mod n to A. That's what we actually want to show, that A is congruent mod n to itself. But we can kind of unpack that a little bit, okay? Let's think about what this really means that we wish. We wish to show that n divides A minus A, because that's what it means to say that A is congruent to itself mod n. It means that n divides A minus A. That's the definition. Both A and B are A. Everybody with me? I.e., well, let's just unpack what it means to say that n divides A minus A. It means A minus A is a multiple of n. In other words, it's n times k for some integer k. That's what it means to say n divides A minus A. And we've seen this sort of thing before, haven't we? We've seen where we had to prove that A minus A was divisible by an integer. We've done this in induction proofs, right? In the basis case. All right, so let's just look at A minus A. Well, what is A minus A, everybody?
0.
It's 0. And isn't 0 equal to n times an integer k? What's the integer k?
0.
0. And 0 is in Z. So n divides A minus A And that means A is congruent mod n to itself, A. So we just proved reflexivity. Every integer is congruent mod n to itself. I mean, there's no jumps of size 4 or n between A and A, right? There's no space between A and A at all. And that's a multiple of whatever, in this case, n. All right, let's look at symmetry. Again, RST123, to prove symmetry, we need two elements, okay? Let little a and little b be elements of Z. Now let's just look at the definition of symmetry. And let's remind ourselves what symmetry says. Symmetry says if A is related to B, then B needs to be related to A. So we have extra hypothesis when we're proving symmetry. We have to assume A is related to B, but here this relation is the congruence relation, okay? So assume A is congruent mod n to B. That's our hypothesis, that A is related to B, because that's what symmetry says. Assume that A is related to B. What do we wish to show? We wish to show that B is congruent mod n to A. So let's think about what that's going to look like. I want to make these a little bigger. Let's think about, what this definition tells us. A is congruent mod n to B. So definition of congruence mod n says that n divides A minus B. That's what it means to say A is congruent mod n to B. So by definition of the congruence mod n relation, A congruent mod n to B means n divides A minus B. That's just the definition. Let's look at our wish. Let's unpack our wish a little bit. We wish to show that B is congruent mod n to A. In other words, we wish to show that n divides B minus A. The order of the A and the B matters in relations. All right, well, let's apply our hypothesis. We know that n divides A minus B, so we get an equation out of that. Let's write this down. Since n divides A minus B, we know, I'm going to put this on a new line because I'm going to label this equation, that A minus B is equal to n times k, right? For some integer k. That's what it means for n to divide A minus B. All right, we're going to call this equation 1. This is what we have in our hand. What we're trying to do is show that n divides B minus A. In other words, we've got that A minus B is a multiple of n. It's n times k for an integer k. What we want is that B minus A is n times some integer. So there's a little algebra trick here. The algebra trick is we can do particular operations on equations. As long as we do the same thing to both sides, it's legal. Except generally multiplying both sides by 0. That's considered silly. But what could we do to this equation so that we could see a B minus A instead of an A minus B? We want to look at a B minus A. What could we do to both sides of this equation so that we could see a B minus A?
Subtract both sides by A.
If we subtract an A from both sides, we're going to have negative B equals n times k minus A. And there is an easier way. You could start like that, and there would be several more steps to do. I'm thinking about an easier thing that we can do to both sides at the same time to change A minus B into B minus A. Can we multiply both sides of this equation by something?
-1.
Yeah. Oh yeah, I see Ronnie said that too. Let's multiply. Multiplying both sides of equation 1 by -1. Well, what do we have? We have B minus A equals negative N times K. And that's almost what we want, but not quite. We're very close. We want to have an N as a factor, not a negative N. So we can just group the -1 with the K. In other words, B minus A is equal to N times negative K. And certainly, negative K is an integer if N is an integer. Do you agree? Certainly, because integers are closed under multiplication. This is multiplication of K times -1. So since K is in Z, we know negative K is in Z. So N divides B minus A, and that means B is congruent mod N to A. And that's what we were trying to show. So it was just a little algebra trick using the equation that we got from our hypothesis that A was congruent to B. Questions? All right, here we go. We've got one more to do. Here's our definition of transitivity. We want to prove transitivity. RST 123. We will need 3 elements to prove transitivity. So give yourself 3 elements. Let little a, little b, and little c be elements of Z. We need 3. And we're going to assume A is related to B and B is related to C. But the relation is congruence mod N. So we're going to assume A is congruent mod N to B and B is congruent mod N to C. That's our hypothesis. A is related to B and B is related to C. Let's think about what we wish. We wish to show that A is congruent mod N to C. Okay? So again, by definition of congruence mod N, A congruent mod N to B means N divides A minus B. And B congruent mod N to C means N divides B minus C. That's just the definition of congruence mod N twice. Well, if we want to unpack our wish, what we wish to show is that N divides A minus C, because that's what congruence A congruent to C mod N means. It means N divides A minus C. Well, we've got these 2 pieces of information, and they yield equations. So let's use those. Since N divides A minus B and N divides B minus C, we have, and I'm going to write them underneath each other. A minus B equals N times K. We can use K again because this was like a little mini proof, almost like proof by cases. That K is done. We can reuse it. If you're not comfortable with that, you can use a different letter, but it's okay to use K again because this is no longer involved with the symmetry proof where K is in Z. And we've got another equation. B minus C equals N times, now here we can't use K again. We got to pick another letter like J, where J is in Z. So we have these two equations. We'll call these equations 2 and equations 3. These are the equations we got from our hypothesis. The definition of congruence mod n gave us these two equations. Everybody with me so far? And now there's one more trick that I'm going to remind you from high school. When we have two equations, there is something that we are allowed to do to both equations. Anybody remember? We're allowed to add them. So adding equation 2 and 3, what do we get? We get A minus B plus B minus C equals NK plus NJ. But look what we're trying to prove. We're trying to prove N divides A minus C. See what happens to this left side? The B's cancel. We have minus B plus B. That's why we added these, because the B's are going to disappear, because we have a minus B and a plus B. So those B's disappear. And then we get A minus C equals, and you can factor the N out on the right side. And we know that K and J are integers, so K plus J is an integer. Since K and J are in Z, the quantity K plus J is in Z. So N divides A minus C, which means A is congruent mod N to C. And that's what it looks like to prove congruence mod N is an equivalence relation. It's reflexive, symmetric, and transitive. And that's actually the definition of an equivalence relation. So the upshot here was congruence mod N is reflexive, symmetric, and transitive. And that's why it induced such a nice partition on Z when N was 4. And so if you just want to look back at that, you can note congruence mod 4 is also R, S, and T. It's got all these properties. Doesn't matter what N is. Okay. So we're running out of time, but I want to go ahead and just look at an example 7 where we let A be a set that just has 4 elements. Because I want to just look at some finite examples this last couple of minutes that we have together here, so that you can think about the fact that we don't have to have a rule to play the game. So here's what we're going to do in this example. We're going to find a binary relation, curly R, on A that is reflexive, is not symmetric, and is transitive. I just want to show you that we can play the game without a rule. We can just make one up. So we're going to find curly R as a set of ordered pairs. We're just going to think about what we need to do to make such a curly R. We need it to be reflexive. We want it that it is reflexive. So the reflexivity says each element in the underlying set has to be related to itself. So we have to put 1, 1, 2, 2, 3, 3, and 4, 4 in the curly R that we're building. We need all 4 of these for reflexivity to hold. So what else? So far, we've got these 4 elements. That gives us reflexivity. We can't even leave one out. If we even leave out even one, we don't have reflexivity. But we want it to be not symmetric. So we need to add something in that's going to make symmetry fail. Any ideas? Remember the definition of symmetry? We need A related to B and B not to be related to A. That's the negation of symmetry. Remember, symmetry was if A is related to B, then B had to be related to A. Well, the negation of an if-then is an and statement, where the hypothesis holds and the conclusion fails. So what could we add into our R that will make symmetry fail? There are lots of choices. The symmetry is okay so far because these elements, these little reflexive pairs, they never blow symmetry because A and B are equal. So if AB is in there, BA is in there for these, you know, when A and B are the same. What could we put into R to make symmetry fail? How about just 1, 2? If we add 1, 2, but don't add 2, 1, then symmetry is going to fail. And I'm just going to leave you with this thought, and you can check it later. Transitivity is never going to go bad if all you have is 4 reflexive pairs and 1 pair that's not reflexive. Symmetry has failed, but transitivity never will if the only non-reflexive pair you have is just 1 non-reflexive pair. So you do later check that transitivity holds. And we're going to pick up our discussion on Wednesday with transitive closure, and we'll start with this, and we'll discuss why transitivity holds, okay? It's time for me to let you go. You've got plenty to chew on. Thanks for playing. Any questions? Thanks, Ronnie. You too. Have a great night. Hey, Nick, I'm going to stop recording.
All right.